Okay, good day, sir. Today, my groupmates and I will be presenting on the case study of explosion and fire in a gas oil fixed roof storage tank taking place at Ashdod Oil Refinery during 1997. I'll first start by introducing the overview of this entire refinery process in Ashdod Oil Refinery. Basically, this is a very simple plant that includes processes like atmospheric distillation, vacuum distillation, stripping, hydrogen catalytic desulfurization, and blending in storage tank. Basically, crude oil distillation process starts from atmospheric distillation, which is based on different boiling points of the hydrocarbon compounds in crude oil, which can be observed from this figure. Then from another figure here, you can see that the temperature yield diagram for the boiling curve of four fractions of crude fractionation, which are the light and heavy gasoline or naphtha, kerosene or jet fuel, and gas oil. So based on this figure, the temperature ranges from 5 degrees Celsius to 360 degrees Celsius. So in this case, the hydrocarbon fractions boiling curve above the 360 degrees Celsius should not be recovered by the atmospheric distillation because the cracking of the heavier products starts above this temperature. Therefore, the atmospheric residue must be subjected to a vacuum distillation. In this case, the vacuum flasher can be used for vacuum distillation, which it can separate the atmospheric residue into a white boiling vacuum gas oil, such as the light vacuum distillate, heavy vacuum distillate, and the vacuum residue. Normally, the vacuum is produced by a set of steam ejectors. Next, let us focus on the side streams comprising of the middle distillate from the atmospheric distillation, which are the kerosene, the light atmospheric gas oil, and the heavy atmospheric gas oil. These distillates are transferred to their respective stripper columns, where the lighter constituents will be stripped off by the injection of superheated steam. So depending on the sulfur content in the crude oil and the level of sulfur required in different gas oil products, these streams will be routed to the HDS unit, which is the hydrogen catalytic desulfurizing unit, together with the light vacuum gas oil for vacuum distillation, or they'll undergo the direct blending process in the product gas oil tanks in the tank farm to produce the diesel fuels. So what is the HDS unit? Basically, HDS unit, known as the hydrogen catalytic desulfurizing unit, is known as a unit to remove the sulfur compounds from the product. For example, sulfur compounds from middle distillate such as gas oil can be removed to achieve the blending qualities for the diesel fuels and the light heating oil. So this HDS unit are also coupled with a stripper column respectively. And in Ashdod Oil Refinery, the blend in the storage tank included streams from various sources, which are the high and low sulfur gas oil from tank farm, the Largo light atmospheric gas oil, heavy atmospheric gas oil, and the light vacuum gas oil from the crude unit, and also the hydrotreated gas oil from the two treatment units working parallel on gas oils. And the product produced will be diesel fuels and light heating oil. So the accident actually happened on the 2nd of November of 1997. On that day of 7 am, the tank was full and was ready for final sampling before dispatching. At 7:30 am, the sample man went to the tank to draw the samples needed for the final testing. A big explosion happened a few moments later. The fires and smoke could be observed immediately from far away. So from this picture, you can observe that the tank 401, actually behind the tank 403, exploded, which the fixed cone roof ruptured and was thrown into the dike. The fire broke out in the dike and engulfed a great part or perimeter of the neighboring gas oil tank 402 with 20,000 m3 capacity. The refinery emergency system started to operate in a very short time to cool a few naphtha storage tank, and the fire was completely put out in 2.5 hours. So in this accident, the sample man was thrown with a roof in tank in explosion and he died. The tank 401 also lost some of the gas oil content and burned in dike. Furthermore, the beams in the tank twisted so much that it could not be used again. And lastly, the sampling device with nylon rope used by the sample man was also split in the explosion. So now I'll pass the presentation to Chun Sing.
Thank you, Hanwei. Now that he has explained to you about the general process, I'll go in depth in the unit operations to share how the problem occurred that caused the incident. So what was the cause for the explosion in Ashdod oil refinery? After kerosene and gas oil is desulfurized, to obtain a more sought-out product, the gas oil and kerosene enters the stripping column. This is where the problem occurred. To understand the stripping column, in general, it can be understood that it is used to remove unwanted materials from the process stream. Fundamentally, stripping columns are governed by the differences in volatility between the impurities and the feed. The more volatile components transfer from the water to the air stream. The air exits the top of the column and contains the most volatile components, while the least volatile components exit with the water at the bottom of the column. There are many types of stripping gas in the industry, such as air, steam, hydrogen. In the diagram, we can see that gas oil enters as a feed, is mixed with the stripping gas. At the outlet, stripped gas is removed with the impurities and volatile components attached, while at the bottom, stripped gas oil which has more desired properties are sent to storage tanks. Initially, when Ashdod oil refinery was running, both strippers started out with using reboiling heater strippers, but in order to save energy, they adapted steam injection. However, this caused turbidity problems. Therefore, it is decided to replace steam with hydrogen. Hydrogen was done because it was available, cheap, and the turbidity problem disappeared. Ashdod successfully done it for about 20 years. 15 years later, the hydrogen stripping also replaced the steam in kerosene stripper. However, the problem for using hydrogen is that hydrogen does not entirely remove itself from the stripping column. With the product and the bypass stream, it also enters the regular atmospheric fixed cone roof, which had open vents to the air. According to simulations done, about 90% of hydrogen were removed from stripping. However, there were also some hydrogen were entrained with the gas oil as bubbles. One day, when the tanks were at maximum capacity at 15,000 meter cube gas oil, there was still 800 meter cube of vapor space in the roof tanks. Hydrogen fills up this roof of vapor space and is present in the tank as a flammable material. There is also air stored inside the storage tank because of the vents. With the flammability of hydrogen being with air at 4% volume to 75.6 volume and requiring only a very low energy, 0.017 to 0.018 millijoule, the consequences of the buildup of hydrogen only needs an ignition source, and it causes the one death, pool fire in the tank 401, ground fire between tank 401 and 402. Next, I will pass to Silke for his presentation.
Now, I'll talk about the safety part of this case study. Israel's oil and gas operations are subject to a complex and varied body of health, safety, and environmental law. Among all the local laws and regulations, the Hazardous Substances Law of 1993 is the major legal tool for the management of hazardous substances in Israel. This law authorizes the MOEP to license, regulate, and supervise all aspects of the manufacture, handling, storage, marketing, and transport of hazardous substances. All the regulations under the law classify hazardous substances according to their use, degree of toxicity, and risk. Licenses are required for any premise selling hazardous substances, and permits are required by any business dealing with hazardous substances. The data provided will help MOEP to widen its supervision and control over hazardous substances found in every industrial plant in Israel. The law also provides various enforcement tools, such as removal orders of hazardous substances and waste. The administrative enforcement measures is important in identifying premises dealing with hazardous substances, compiling information on the types and quantities of hazardous substances, and ensuring that safety procedures are strictly observed. For the penalty, contravention of the law or its regulations carries a fine, 6 months imprisonment, confiscation of the articles in respect of which the offence was committed, and withdrawal of the permit. An authorised representative of the MOEP may enter any premise handling hazardous substances for the purpose of inspection or investigation. Samples may be collected, and the representative may prohibit the sale of certain hazardous substances until the completion of the investigation. Next, I'll talk about the compliance of Ashdod refineries with local laws and safety practice. After reviewing the details in the laws and regulations section, it is clear that Ashdod oil refineries had actually complied to most of the local laws and regulations. Firstly, they had efficient emergency procedures. It can be seen by the refinery emergency system that started to operate rapidly after the accident happened. Next, their decision to use foam on the roof completely put out a massive roof pool fire. The surface cooling systems also enabled protection of a number of naphtha and other product tanks nearby. Secondly, we can see the sample man wore proper PPE, which includes anti-static clothing and safety anti-static shoes. Thirdly, the process was held under safe operating conditions. This could eliminate the possibility of liquid charging with electrostatic charge, which is done by waiting for the liquid movement during filling for almost 10 hours until sampling was done. However, Ashdod refineries lack of hazard review. In this case, it is impossible to reduce all hazards in a hazardous chemical system, but all the risks in the system should be identified. The refineries had never performed hazard on the main gas oil systems flowing from the bottoms of the two HDS strippers with hydrogen stripping. Moving on, for the first safety suggestion, it is about the responsibility of the authorities. During the investigation after the event, it was found out that an important 1995 standard stated that nylon or polyester rope should be used to reduce the potential for static charge. It was found out later that a typing error was made by missing out the word not after shoot word. Since it was reported that the most probable ignition source was an electrostatic charge on the sampling device rope, which was synthetic and not cotton, this error was fatal. If the authorities had given more checking on the standards implemented, such incidences might be avoided. Secondly, I'll talk about the mechanical integrity. Modifications can be made. For example, fixed roof tanks can be constructed as weak seam roof tanks. By doing so, the damage will be much lower by preventing the spread and burning of the contents inside the tanks if a fire or explosion occurred. So what are weak seam roof tanks? This is defined as the design so that the roof to shell connection will fail preferentially to any other joint, and the excess pressure will be safely relieved if the normal venting capacity should prove inadequate. In conclusion, although Ashdod Refinery complied to most of the regulations and acted well during emergency, accidents such as fire and explosion still occurred. Therefore, precautions such as hazard analysis should not be taken lightly, as there are many hazards in these industries that needs to be kept under control. That's all for our presentation. Thank you.